Okay, I'm going to try this again. I've been trying to record all evening and it keeps messing up. I don't know really what's going on, but well, hopefully this will record. So this is Math 12A. We are starting into Chapter 7. You have an assignment that is due March the 30th on sections 5.5 to 5.7. That's going to work sort of as your unit test and your assignment together. I am going to have to play with the weights a little bit on like how much each category is worth. So please make sure that you are handing in your homework, any assignments, even if the assignment is just to watch a video. Please make sure that you hand that in the upper right corner in Google Classroom. Please be handing things in through Google Classroom, not through email, because what Google Classroom does is it keeps track of it for me so I don't lose it on you, okay? So right now what we're doing is we're going to start into Chapter 7 on page 386. Chapter 7, like I said before, is really on geometry. We went over some theorems out of Chapter 6 in the last video. Section 7.1, probably most people's least favorite section ever. Like I said, don't judge all of Chapter 7 on this first section. We'll get through this first section. Again, I will probably condense it a little bit from what we would normally do because of the format, because it's not as easy just to take questions and answers. So section 7.1 is on geometric proofs. This is really what geometry is all about. This is really the basics of geometry, is doing geometric proofs. So what I have on the board is example 1 on page 386. I am never going to have you do a geometric proof right from scratch. I will fill in part of the proof, and there will be blanks that you will have to fill in, but you will never have to give one right from the get-go, right from the start. And we're going to do them right from the start here. Now they give lots of different ways to give a geometric proof. We're really going to stick to this first one, this first way of doing it. I'll explain kind of the other ones, but we're going to stick to this one. It's the most traditional, and it's probably the most straightforward. So in example 1 on page 386, what it says is it gives you this triangle, and it says prove. So we have to prove it. Prove that angle A, B to D, so that would be this angle right here. Prove that it's equal to angle CBE, so that would be this angle right here. We have to make statements and reasons of a logical proof as to why this angle would actually be equal to this one. Usually it involves proving that a couple of triangles are congruent, because if you can prove that the triangles are congruent, then everything about them is the same. The sides are the same and the angles are the same. So generally what a geometric proof looks like is there will be a statement here, and we will give a reason why we can say that statement over here. This is where things like theorems and things like that will go, is in your reasons. So we're going to make a statement, and then we're going to give a reason why we can say that statement. And again, what will happen on a test, on an assignment, on something like that, is I might fill in a statement and you have to give what the reason for that statement would be, or I might give a reason, and based on what that reason is, you have to say what the statement is. It'll be fill in the blank. But because we're doing it together, we can go right from scratch. So the first statement that they say is they say BD is equal to BE. So BD, this line right here, is equal to BE, this line right here. The reason why we can say that is probably my favorite reason, because it's the simplest one. Notice they put, I didn't make this up, the textbook has it. They put 2 little ticks on this line and 2 little ticks on this line, basically telling us that those 2 lines are the same. So the reason that we give is given. That information was given to us. We didn't have to think it up. We didn't have to come up with a reason. They just told us so. It's my favorite one. Then they say that angle BDE is equal to angle BED. So let's look at where those angles would be. BDE, BDE. This angle right here is equal to angle BED. This angle right here. Now, they didn't give us that in the original picture, but yet they're saying it. So why is it that they know that those 2 angles are the same? Well, in the last video, we talked about isosceles triangles. And we said in an isosceles triangle, the 2 opposite sides, if those are equal, then the 2 opposite angles are equal. So the reason that we give, and I'm going to shorten this, I'm going to use shorthand here, is the isosceles triangle theorem. The isosceles triangle theorem would tell us that if we know opposite sides are equal, then the opposite angles have to be equal as well. So then they make another statement, and they say angle BDA. So let's figure out where that is. BDA, this one, is equal to BEC, this one. Now the reason that they give is not a theorem that we've picked up anywhere, it's just logical reasoning put into math lingo. So let's talk about the logical reasoning first. This angle and this angle would have to add up to 180 degrees because that's a straight line. So they would have to be. So if this was 40, this one would have to be 140 in order to add up to 180. So these 2 angles are supplemental because they add up to 180. Same thing over here. This angle and this angle would have to add to be 180 because they make a straight line here. So if we know that these 2 angles are the same, and we know that this one has to add to this one to give me 180, and this one has to add to give me this one has to give me 180, then it only makes logical sense that this one is equal to this one. But how do I explain all that using math language? Well, here's what they say. Supplements of equal angles are equal. So it's a long explanation, but supplements, meaning angles that add with the other one to give you 180. So supplements of equal angles are also equal, and that's just logical reasoning. If you didn't put it in such proper math terms, but you said they both have to add to be 180, that would work for me. Then they say BA, I didn't finish this over here, sorry. BDA is equal to BEC. I didn't finish the statement, I don't know why. So the next one they give us is BA equals BC. So BA equals BC, right there. And again, they put the lines there. So basically, my reason is given. And then they say angle BAD. So let's look at where that is. BAD. So that's this one right here. Let's call it, I don't know, A. is equal to angle BCE. So that's this one right here. And again, why can we say that? Because it wasn't given to us, but they did give us that these opposite angles, opposite sides are equal, which according to the isosceles triangle theorem means that this big triangle here is an isosceles triangle. So these opposite angles would have to be equal. So again, I would say the isosceles triangle theorem. And I'm lazy, I don't want to write it all out. Then they say angle ABD is equal to angle CBE. Now up here, remember, that's what we were trying to prove. We were trying to prove that this angle is equal to this one. Now why can I say that? I can say that because of something that, again, they tend to put stuff in here that they haven't talked about before. They do that so that you'll learn it as you go. This is something called third angle theorem. And here's what we mean by that. See, in this little triangle here, I proved these two angles are equal to these two angles. Well, if all the angles in a triangle have to add up to 180, and I know that this is 50 and this is 40, that would be 90, then I know that has to be 90. Obviously it's not, but that's what it would be, right? And same thing here. So the third angle theorem basically says, if you can prove that two angles in one triangle are equal to two angles in another triangle, then the third angles also have to be equal. Again, it just makes logical sense, but they call it third angle theorem. So that's example 1. Again, what I would do is I would leave blank. So I might leave that reason blank, but give that statement. I might leave this blank, but give that reason. So I'll leave blanks in there that you will have to fill in. You'll see what I mean when I give you the homework. Okay, example number 2 is going to introduce to us some new theorems. So it's really important that we do this one. And they give us a line here and a line here, and they give us a little right angle triangle. They give us A, B, C, and D, and they put a point P here. Now we have to talk about some language that they're going to use, okay? They say prove that any point on a perpendicular bisector of a line segment. So they use this word, these words, perpendicular bisector. All that a perpendicular bisector is a line here that is perpendicular to another line, and bisector means that it cuts it directly in half. If it's a bisector, it automatically means that this line is halfway in between A, B. So C would be halfway between the A and the B if they're telling us that that DC is a perpendicular bisector to AB. So they want us to prove that any point on a perpendicular bisector, so here's a point, is equidistant, which means equal distance from the endpoints of the segment. So what they mean is any point that I pick, so if I pick this point and I draw a line to the end of this line and a line to the end of this line, prove that those are equal, okay? Prove that. So basically, what we want to prove is that AP is equal to BP. Basically, that's what we want to prove here, all right? They do this in a flow chart proof, but it's the same thing. It's still a statement, and a reason. I'll do it as a flow chart just to show you the difference, but you're still making a statement and a reason. It's not giving it in a list format. So the first thing they say is that AC is equal to BC. And we have to give a reason for that. Now they put a box around it because that's our statement. In a flow chart, this is how we do it. Now we have to put a reason underneath it. Now they just put the word definition, but I'm going to put definition of bisector. Because if they're telling us that this line is a bisector, the definition of a bisector means that this side and this side have to be equal. So definition of a bisector, that's why I can say that. Then they say angle ACP. ACP, this one, is equal to angle BCP. So this one. And again, that's a statement. And why can I say that? Again, they just put definition. I'm going to be a little bit more specific, and I'm going to say definition of the word perpendicular. They told us perpendicular. They told us it was a perpendicular bisector. Well, if it's perpendicular, then it's 90 degrees on that side and 90 degrees on that side. Then they say PC is equal to PC. So why are they making a stupid statement like that? Well, because this is really two triangles. It's a triangle on this side, and it's a triangle on this side. And that line PC is part of this triangle, but it's also part of this triangle. It's part of both of them. This is my second favorite reason, again, because it's easy. This is something called the reflexive property. You'll want to remember that one because it's going to come up again, and it's a great one because it's easy. If the line is part of both shapes, then it's the reflexive property. All right, now what they're going to say is they're going to say, listen, I'm going to take this reason, I'm going to take this reason, and I'm going to take this reason. Now, notice what we did. We did a side and an angle and a side, okay? We did a side, an angle, and a side. And we did, so we did a side, and this angle in the middle. What we did was we did this side, and this angle in between. So we can now make a statement that says triangle ACP is congruent. And congruent is an equal sign with a little wavy line over it. Is congruent to triangle BCP. So that's a statement, so I put a box around it. Reason is because I did a side, an angle, and a side. Way back in grade 9, there were 3 ways that you could prove that a triangle was congruent. Side, 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 angle, side, and angle, side, angle. So if I've now proven that these triangles are congruent, congruent means that all the sides are the same, all the angles in corresponding are the same. That means that I can now say, and I'm running out of space, but that means I can now say that AP, this line here, is equal to BP. And why can I say that? Because I just proved that I have congruent triangles. So this is what a flow chart would look like, but I could have just as easily made a list of statements and a list of reasons. It's the same thing, it's just how the presentation is. Some people like a flow chart better than a list of statements and reasons. It doesn't really matter to me. Sorry. Oh, this is erasing. Great. Okay. Oops. Example, let me see. What example do I want to do? Yeah. I'm not going to do example 6 for sure. I just want to make sure that reflexive property, I covered that. Okay, let's do example number 3. Example number 3, they give us a parallelogram. And they give us that this is A, B, C, and D. They tell us this side is the same as this one, and this side is the same as this one. And they want us to prove that AD is parallel. In the textbook, they don't use the words. They say AD, and they put 2 parallel lines, meaning is parallel to BC. So we want to prove that AD is parallel to BC. The 2 ticks here tell us that they're equal lengths, but it doesn't tell us that they're parallel. So they want us to prove that they're parallel. Now this time they do a paragraph proof. And again, if you want to see that, it's on page 387. But I'm going to go back to the good old statement and reason. Just because I find the paragraph proof isn't very clear. Now I've had problems recording today, so I'm just going to take 1 second to go and check and make sure this is still recording. It says it is. I'm going to believe it. All right. If it's not, I don't know. I'm going to have a fit. But anyway, so we have to prove that AD is parallel to BC. So how are we going to do that? Well, the first thing we're going to do is we're going to draw a line right through here to create 2 triangles. That's what we're going to do. You're allowed. And now we're going to make some statements. Now the reason why I wanted to do this one with you is because it brings in some theorems that we talked about from chapter 6. So the first thing they give is that AB is equal to CD. AB is equal to CD. Reason, that one's easy. It was given to us. They told us that. It's my favorite reason because it's easy. They also say that AD is equal to BC. Reason, still given because they said this and this are the same length. So that's great. And they tell us that AC is equal to AC. Again, this line is part of this lower triangle. It's also part of this upper triangle. So that's my second favorite reason. That is the reflexive property. Okay. And so because I've proven a side, and a side, I can now say that triangle ABC is congruent, so that's that equal sign with a wavy line on it, to triangle ADC. The reason, side, side, side. So I've proven that the triangles are congruent. So if I've proven that the triangles are congruent, I have proven that angle DAC is equal to angle BCA. So DAC, so this one right here, is equal to BCA. So this one right here. So let me pull out a different color here for a minute. Think back to yesterday when I talked about the Z rule, the F rule, and the C rule. And notice that this makes a backwards Z. And it said if a transversal goes through 2 parallel lines, then the alternate angles are equal. Well, you can kind of reverse that and say if the 2 alternate angles are equal, then you know that those 2 lines are parallel. It's the transversal parallel line theorem. It's the Z rule. So we'll call this the transversal parallel line theorem. Now you may not have thought of that on your own, that's why I'm here, okay? But that's how you would go about doing that. I want to go through, I'm going to go through I'm going to go through in depth one more with you. And then I want to talk through, so you're going to need to open your textbook so that you know what I'm talking about, okay? Maybe not, maybe I won't go over it. Example 4, I want to go over. Sorry. I'm just trying to decide if I want to. No, I want to do example 5. Example 4 doesn't have anything really new in it. So I want to go over example 5, even though I don't like it very much. I want to go over example 5. So it gives us 2 triangles. They're both right angle triangles. And they give us ABC and this side and this side. And then they give us DEF. And this side and this side. And what they want us to prove is that triangle ABC is congruent to triangle DEF. Now, we already know 3 things. We already know that this side's equal to this side's equal to this one, and this angle's equal to this one. But that is not side, angle, side, because this angle that we know is not in between the 2 sides that we know. So the reason why I want to do this one is because they bring in a couple of things that they haven't talked about before. So that's why I want to do this one. I don't really like it, but we're going to do it anyway. So we're going to be using the idea of Pythagorean theorem, okay? So they say let AB equal DE and let that equal S. In other words, AB and DE, we're going to give it a letter. We're going to call this side S and this side S because we know they're both the same. And they're going to do the same thing with CA and FD. They're going to call this side T and this side T just to make things a little easier, okay? So they say, one of their statements is, in triangle ABC, so in this triangle, T squared is equal to S squared plus BC squared. So this side squared is equal to this squared plus this squared. So my reason, it's the Pythagorean theorem. That's the only reason. That's all I did was state the Pythagorean theorem. And so then what they do is they rearrange this statement. They bring the S squared over here, and they say T squared minus S squared is equal to BC squared. So all they do is rearrange the formula. They subtracted S squared on this side, and they subtracted S squared on this side. So in fancy geometry terms, rather than saying I just subtracted the same thing from both sides, they call that the subtraction property, which again is just a really fancy way of saying I subtracted the same thing from both sides. It's like geometry just likes to make things sound complicated. We're going to do the same kind of thing for the second triangle. In triangle DEF, t squared is equal to s squared plus ef squared. And again, the reason is Pythagorean theorem. That's just Pythagorean theorem stated, that's all. Then I'm going to rearrange it. I can say that t squared minus s squared is ef squared. And again, that's just the subtraction property. I just subtracted the same thing from both sides. Now, then what they do is they say, based on everything I have up here, so if bc squared is t squared minus s squared, and ef squared is also t squared minus s squared, then I can make a statement that says bc squared is equal to ef squared. Now, there's a fancy word for that. When I make a statement and I see that this and this both equal each other, so I can say that this is equal to this, there's a fancy word for that. It is called the transitive property. Okay, it's just a fancy word, transitive property. And it means that if this is equal to something and this is equal to that same something, then these two have to be equal. It's really just logical thinking, okay? So, if that's true, then if I took the square root of both sides, I could say that BC is equal to EF. And again, to make it complicated, because it's geometry, they call that the square root principle. Basically, if I take the square root of both sides, then those two are equal. So, I basically now can say that I have proven that this side is equal to this side. We already were told this side is equal to this side, and this side is equal to this side because we were told that. So I can really say that the two triangles are congruent because of side, side, side. So the reason I would give would be side, side, side. So I'm not going to go over example 4 or 6. There's nothing really in it that you need. So I want you to do, and I'll put this on Google Classroom, I think it's, I'll double check, but I think it's numbers 1 to 4 starting on page 389. And again, they fill in some of it for you, and you have to fill in the blanks in the appropriate places. And that's how I would ask it on an assignment or a test. You will not be asked to completely generate a proof with nothing to go off of. Sorry this one was so long. Hopefully the next ones won't be as long. But I knew I had a lot to go over with that. So watching the video should take a whole lot longer than the doing the homework, okay? So we'll talk to you again soon. Bye.